Hello, students. The time has come to discuss mixture distributions. Now, note sometimes they're called compound distributions, but I will try to stick to mixture distributions here, especially because we're going to use compound distribution for something else that is going to have a different meaning. Now, also, don't confuse this with mixed distribution. It's a completely different idea here. And so, in fact, a mixture distribution is not really a type of distribution in the sense of a continuous or discrete or mixed. It's a more way to create new distributions in two easy steps. So first, consider that x, a random variable, has a certain density or mass. Now, here I'm going to use a notation for density. So assuming that x is continuous, so has a density little f, but this works as well if x is discrete, so as a mass. But here important, what I call fx given theta is a conditional density. So it's as you would have seen in your probability courses, a density, but conditional on some information. Well, conditional on the information, theta equals the specific value little theta. And so, and here theta, so here big theta is a parameter in the distribution of x, but it is considered to be random, so it has a certain distribution. So theta is a parameter in the distribution of x, but it is itself random. And because it's random, we can give it a density, here denoted g of theta. In fact, it could be a discrete random variable as well. So theta could be a discrete random variable, in which case it would have a mass. But for now, let's assume that theta is continuous, so it has a density g theta. Now, by the way, this sounds maybe a bit abstract, but in a second we'll see a specific example that I think will help understand. So that's but for now, that's the first step. Just consider that x has a conditional density, conditional on knowing the parameter theta, which itself is random, so has a density g theta. Now, the second step is to obtain the unconditional density of x. And this is given here. Well, density or mass, but here we assume with the notation little f, we kind of imply that it's a density, but it could be a mass. So we could have, what I mean is we could have a p here, could have a probability mass function, it works as well. Okay, so this is given here. You integrate the product of the density, sorry, the conditional density with the density of theta. But now note the following. This thing, the product of the conditional times the distribution of theta is in fact the joint distribution of x and theta. This is, I hope, a familiar result from probability. This would be the joint density of x theta evaluated at little x and little theta. Okay, and you know, I hope you know, or if not, I guess it's not the end of the world. I remind you that when you integrate this thing, which is a joint density, when you integrate with respect to a specific variable, here theta, you obtain the unconditional density of the other variable, in this case x. Okay, this is again a standard result from probability. Integrate the joint with respect to one variable, you get the unconditional density of the other variable. And of course, here the integral would be taken over the whole support of theta, all the possible values of theta. Now, if this theta is discrete, this technique works as well. You would simply, because then if theta is discrete, you would have g theta would be a probability mass function. And so you would replace the integral by a sum. So you would sum the fx given theta times p theta over all the possible values of theta. In fact, the example we're going to see in a second will be an example of that specific case. Theta will have a discrete distribution. Okay, so we'll see an example, but before, let's just interpret what's happening here, because again, what I said is this is a way to define new distributions. Let's review the interpretation. So for such mixture distributions, you could say that there's two steps of randomness. So the final outcome, because here we're creating a new distribution, fx. So there's going to be one final outcome, an observed value of this random variable if you observe the random variable. But for this final outcome to happen, two things need to happen. I call this two steps of randomness. The first step is that the parameter theta, which is random, will be randomly generated and will take a specific value. Now, the randomness of theta is characterized by the function g theta. So first step, the random variable big theta is observed, so you obtain a specific value little theta. Once this happens, then the second random step happens, and this is when the little x value is obtained, is generated, but according to the conditional distribution little f of x given theta. Okay, so once you have generated your theta, this distribution, the conditional distribution of x given theta, generates the final outcome, little x. But now, if this process was repeated a very large number of times, meaning each time you generate a new theta, and this theta is used to generate a new x according to the conditional distribution of x given theta, imagine you do that several times. So you have theta 1, theta 2, theta 3, theta 4, blah, blah, blah. And theta 1 is used to generate x1, theta 2 is used to generate x2, theta 3 is used to generate x3, blah, 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 up to theta n is used to generate xn. Now, those x's, their theoretical distribution is the distribution, the unconditional distribution fx. Okay, so if you were to grab this, imagine you've done this a large number of times. Now you have all those data points. The empirical distribution of those data points would resemble the unconditional distribution fx, where fx is, of course, it's a theoretical distribution. You have this is an expression of it's a function of x, so it's a theoretical distribution. Okay, I don't know if you've if this is a bit hard to follow because it's quite theoretical, but let's see an example. Hopefully, it's gonna help out. And of course, it's an example involving our friend Josephine. And she's still looking for love. Now, what's happening here is this. And by the way, here, y will play the role of our theta. So imagine that y, it's a Poisson random variable, and this here denotes the number of likes Josephine receives on a dating app per week. So simple enough, y is the number of likes, it's a Poisson. So if she's unlucky, she gets 0 likes, but she might get 1, 2, 3, 4, blah, blah, blah. Now, each time she receives a like, this like can lead up to a date. Okay, maybe she's going to match with this person, and then maybe she's going to go on a date with this person. Now, we consider here that this happens with a fixed probability, little p, meaning that every like can potentially generate a date, but this doesn't happen all the time. So there's a probability that a like leads to a date, and we call this probability little p. Okay, and independently here, we do need the independence assumption, meaning, yeah, she gets a like from somebody. There's some probability she goes on a date with this person, but then she goes on dates, independently of for each like received. That's the setup. Now, first question: if now we call big X a different random variable, simply the random variable for the number of dates stemming from all the likes she received in a week. What is the conditional distribution? So conditional for now. What is the conditional distribution of X given this Y? Again, Y is the number of likes. X is the number of dates stemming from those likes. What is the conditional distribution here? And here, independently is a keyword. Take a second, think about it. Well, hopefully you see that it's actually just a binomial, because you conditional on a certain fixed number of likes being y. Every like can lead to a date with a certain fixed probability p. We consider that those are independent trials, so you're just counting the number of successes out of y trial. This would be a binomial, which I believe should be written here. Yes. conditional on y being equal to a specific value. X is counted the number of dates out of y independent trials. So the conditional distribution is here. X given y took a specific value, little y, is a binomial. With parameters, of course, number of trials, little y, and probability of success as before, little p. So you see, this is an illustration of what I meant here. 2 layers of randomness. First, she randomly gets a certain number of likes, and then second layer of or step of randomness, out of those likes, she gets a random number of dates. But the distribution of those dates given the likes is known. It's a binomial here, provided the assumption of independence and fixed probability p are met. Now, second question, that's a bit more, we're gonna need a bit of mathematics here, a bit of derivations. Derive the unconditional distribution of x. So you know that x given the number of given y, given the number of likes, is a binomial. But what is the unconditional distribution of x? Meaning, if you don't know the number of likes, so you don't have any information about the likes, what is then the probability, well, the distribution of x, the number of dates? Meaning, we're looking for this here, unconditional distribution of x. Well, let's do the calculation. And again, here, we are in the case where our y, or in the notation here, our theta is discrete, because the number of likes, of course, is discrete, a Poisson. So we're going to sum over the mass of y, and also this the number of dates is also discrete. So it's a discrete. So everything is discrete in our example. But this illustrates that it works for either discrete or continuous. And here, I think it's clear enough. But both the x and the theta can be either continuous or discrete. Here we have 2 that are discrete. Okay, let's do the calculation. So it's pretty much a direct application of the formula, but we just need to be careful that here it's a sum, and we need to pick the right bounds for the sum. So what we're looking for really is this: the probability that x, the number of dates, equals a specific value, little x. And our calculations will be valid here for any little x. Okay, so as x, you just assume it's a generic argument. It can be 0, 1, 2, blah, blah, blah. Now, you then sum the conditional. So you sum for all the possible values of the y, you sum the probability that x, the random variable, takes the specific value little x, but conditional, of course, on y being little y times probability that y is little y. But now, just careful here, we're summing for all the values of y, but that go from x to infinity. Well, yes, take a second to convince yourself of this. X is always smaller than y. If I got well, not I, but Josephine, if Josephine got 10 likes, the very maximum number of days will be 10, because that's the maximum, right? Of course, if she's very lucky, maybe every like will lead to a date, but that's the maximum. So this is why you see the probability that x equals x. Well, what's the probability that x equals x y plus 1? Okay, if y equals y, well, this is 0. She cannot get more dates than likes. Okay, but then the second y, so the first y in the summation will be x, so that's fine. If she's very lucky, she's gonna get little x dates out of the little x y she got. Then the second term in the summation will be for y equals x plus 1. Obviously, that's also fine. If she got x plus 1 likes, she might get x dates out of it, and etc. And there's no theoretical bound here. She could get she could get infinity, or a super large number, 1,000 likes, and in which case you would find the probability that she gets X dates out of those likes. Okay. Hopefully that's clear enough. And then the rest, frankly, is just algebraic manipulation. Let's go over them, make sure we understand every step. So this Y is a Poisson, so the good old Poisson with parameter whatever lambda. I think it's not specified in the question. So yeah, let's just have the lambda here. Now, X given Y is a good old binomial. So again, this is known. The probability to have X success out of Y trials is just combination of X and Y, then P to the X, 1 minus P to the X minus Y. Sorry, Y minus X. And then what else? Careful here that, of course, it's the Y, the summation is with the index of the summation is Y. So everything that has to do with X, you can put it outside. It's not affected by the summation. So it's seen as a constant in the summation. So you can put this thing outside. Same thing, this thing is a constant, you can put it outside. Now what remains? Here we just made a simplification. We call 1 minus P, we call this Q. Maybe it's not that useful to do that, but why not? Then what else? That's the same, that's the same. Okay, so from this step to this step, it's just a little simplification. Now what else do we do? Okay, we're going to put this thing, we would like to put it to the same power of this thing. So we do a little trick. We just multiply lambda to the minus X times lambda to the X. So you see here I've just multiplied by 1. One of those lambdas to the X, this one I will put it outside. So what remains here is lambda to the Y times lambda to the minus X. So you can say that it's lambda to the Y minus X, which matches the power here. So you put everything together. Lambda Q to the Y minus X. And then what else? This term we have developed, I think you know that combination of X and Y is Y factorial divided by X factorial divided by Y minus X factorial, which explains, yeah, okay, well, this Y factorial is canceled out by this one. How convenient. And the other two are found here. Okay, hopefully that's all clear. And we can go to the next page. Now here, well, realize if you have I don't know, a strong kind of mathematical intuition, you might smell that we're gonna have a nice simplification involving the exponential, because we have something to the power of the index in the summation, and then we have the same index to the factorial. So that really looks like we're gonna use the exponential. We just need to make a change of variable, which is what we do over there. Call this thing Y minus X, call it S. Okay, Y minus X is here, Y minus X is here. Realize that because you start the summation at Y equals X, you see the first term here really in the summation is 0. So if you call Y minus X S, well, it's nice. You're going to start your summation at 0 and you're going to simplify the expression. So you do that. What has happened here? We just put the X factorial in front, because again, it doesn't depend on the summation. So this X factorial, we put it in front over here, well, in front of the summation. And here, that's what I said. Now I hope it's obvious. This is e to the power of whatever this thing is. Yeah, that just by definition. In case you don't remember, e to the x is by definition the infinite sum starting at 0 up to infinity of x x to the k divided by k factorial. Okay, so this is what we use over here with x. Well, here maybe it's poor notation because we already have had something for x, but you'll forgive me for this. Let's call it something else. Let's call it w. Okay, and the W would be here just lambda q. Okay, so we have e to the lambda q. And then what else? I think we're pretty much done, right? Yes, we have here e to the lambda times e to the lambda q becomes e to the lambda p. Maybe they just write that explicitly to make sure. E minus lambda times e to the lambda q. You can put minus lambda in front, then you get 1, then here you get minus q, which is then e to the minus lambda p, which is what you found. You find this thing is here, the rest doesn't change, and you're done. You're done. You realize this is very nice. Simply the PMF priority mass function of a Poisson with an updated parameter now, lambda p. You see? Lambda p. Yes, indeed. This x, the unconditional x, is nicely a Poisson lambda p. So with a new parameter lambda, of course. So the result, just to summarize, is that the number of likes was Poisson lambda. Now every like can lead to a date with a fixed priority p. Turns out, then the number of date is itself Poisson with parameter not lambda but lambda p, which is a nice theoretical result, I believe. Well, at least it's elegant. And I suppose that's the end of the video, so I'll stop here. Thank you so much for listening, and I'll see you soon, I hope. Bye-bye for now.